So the next thing is the development process. Most important step is the testing of the code. If you guys have already worked with the FPGA board, then you would have seen that whenever we write the code, after writing it, it synthesizes. During the synthesis, it checks the syntax and then it makes a netlist. After that, we go to the next state, implementation, place and route, and then we go to the generate bit stream, and then we make a connection to the board, then download it, and then we check it with the buttons and with the LED. Each of the update in your code, I mean, at least take 3 to 4 minutes to check the output. And this is in the case when your design is extremely simple, only flip-flops kind of things. So at every time, whenever you write the code and test it on your hardware, it takes so much time because there are so many steps involved. Synthesis, place and route, generate bit stream, and then putting on the FPGA board. And if you have performed any kind of logical or I mean functional errors in your code, this is really bad as far as the timing is concerned, because every time it will take so much uh, time in every step, so your time will be lost. Development timing will be extremely high. So this is a really bad approach when your design is complicated and you are not sure about the validity of your code. So before you go, after writing the code into the synthesis and the next step, you always want to verify your code by using these kind of simulation, what you have really seen in the previous slide. So just after the design entry, just after writing the VHDL or Verilog code, you perform the simulation before doing any other thing. So first we do the simulation. If everything works fine, then we go to the synthesis step. And if something goes wrong, the simulation shows that my input and output relation is not what I intended, not like what I desired, then I will go back, changes according to the error in my code, and then perform the simulation again. And whenever it is fine, then I will go into the next step, synthesis, place and route. In the advanced design, we also do the last time simulation. And before, because we have put some condition in the place and route and also in synthesis, and if bad thing happens, then we can go back. I mean, now we will see the simulation only at this part, but we can perform the simulation either just after the design entry and also after the place and route, because these steps might also introduce some sort of the undesired effect in my output. But our design, for our design, we will do only the simulation just after the VHDL code entries. The idea of simulation at both steps are the same. So how we will do the simulation in VHDL? For example, when you write the code into in C or C++, and you have to see the output, what do you do, guys? I mean, you write a code in C and C++ or in Java or in Python, then to check the code is right or wrong, normally what do you do? Come on, guys. For example, you are running the code on the processor and you have to see the output. Then what do you do? Come on. So you use kind of printf statement, printing on the screen. Provide the input and see the output directly on the screen. I have one answer. It says, yeah, assertions and report if there is something wrong. That's fine. This is also a kind of thing that you see something on the screen. In the VHDL, we do the simulation. And how this simulation are done. The concept of checking the output is a little bit different in VHDL as far as the simulation is concerned. So when we have the simulation desire to, performing a step, there we have, uh, some sort of verification file. So one VHDA project contains a design file. This design file contains your logic, whatever you wanted to implement, your VHDL code or the Verilog code for doing functions, loops, process, whatever you wanted to do. This is present inside the design file. Corresponding to the design file, we have a verification file. This verification file is also called TestBench. So whenever we perform a simulation in VHDL, of course, we have a design file, the file which we write, which we want to test, which has our logic. Beside this file, we also a testing file. This file is also called verification file, or in terms of RTL, it's called test bench. This is a little bit difficult to understand that, man, to check my VHDL code, I have another file. So let's see with the example. This is the most simplest example I could have presented. So for example, we have a bulb, electric bulb. Consider it as a VHDL code. And this electric bulb has input, and input are the plus minus present on the circuit, internal circuit present outside on this aluminum or whatever structure it is. And then the output is the luminosity or the brightness of the bulb. So then consider it as your VHDL code. And this VHDL code, to test it with the test bench, you need a test bench code. This test bench code in terms of this bulb has some sort of, you know, kind of place where you will put the bulb. And then it has also some signals which will map the signals of your bulb. So bulb have plus and minus. This test bench or a holder also have a plus and minus. So whenever you have to put the bulb for testing, you will put it on this kind of test bench, and then this test bench will map the plus of this bulb to the plus of this holder, and the minus of this bulb with the minus of this holder. And then after that, what you will do, you will apply the plus minus electricity signals, and there, the if the bulb goes, that means the bulb is, the simulation is fine or test is fine. Otherwise, the VHDL code or the bulb in this case is not providing us the real functionality. So this example really fits into the concept of the VHDL simulation. So VHDL code is represented with a bulb, test bench with this holder, and then when you will apply the plus minus, so here we will have the input signal, and this putting the bulb on this holder is called port mapping. You will mapping the plus with the plus, minus with the minus. This is exactly what we have in the VHDL. We have VHDL code, test bench, port mapping, and this applying of the signal, which is called stimulus. So this is the concept of testing the VHDL code with the simulations. So we will have a VHDL code which is called design, or it is also called design under test, DUT, or it's also called UUT, unit under test. And then we have a test bench which contains all the, you know, things to put this code on this test bench, which will map its signal with its testing signal. And then inside this test, we will apply some stimulus, plus minus. So we can check the code. This is the concept of doing simulation. Please keep this in mind. VHDL code, test bench, port mapping. VHDL code is the code that you develop, design under test. Test bench is a place where you will put your code. Port mapping is the process where you will match the plus with the plus and minus with the minus between the boards and between the bulb and its holder. And when you apply the signal, this is called stimulus. So code, test bench, port mapping, and the stimulus. Code is a design under test. Test bench is a place where you will put your design to test. Port mapping is a place where you will join the ports of the input and out of the design and the test bench. and stimulus is the place where you will apply the plus minus. So this is the thing that we are going to have: VHDL code, test bench, port mapping, and stimulant. Let's see now it in real action. So we have test bench, design under the test, and then here we have generation of the stimulus to apply a plus minus, and this plus minus will be connected with the device under the test, and then we will see the result on the uh, uh, graphical chart or the simulation. So we will put the unit under test or design under test on the test bench, and then we will see the output in the form of the timing diagrams. So let's see in a most simple way. So far, the first example that you have tested was the AND gate, what I have given to you in my slides. So we have a simple AND gate which has two inputs and one output. And then we have one statement that input one and input one and input two were ANDed together, and then the output was created. Let's see whether this code was working or not. So as I told you that to test it, you will have to write the test bench, and this test bench is also the VHDL code. And sometimes the length or the size of this test bench is bigger than the size of the actual code. As you can see, this is the actual code of my AND gate, and this is the test bench of this AND gate. But this test bench is very, very simple. There is not extremely complicated logic. It's a very, very simple logic that we need. And remember, with this example, what we need: a test bench which should have plus minus. So a test bench which will have these signals plus minus, a port mapping which will map the signals of this bulb to this port, the signals of this holder, and then later we will apply the plus minus. Remember this thing in your mind. So here in the test bench we have some entity, and then the component is placed, as you can see, internal signal on this test bench, and then we will map them, and then we will apply the stimulus plus minus, wait for some time, change the label, next signal, testing, and wait, and then 0 1. When we wait some at this point, we will see the output label in the graph area of my simulation. So this is the test bench of my AND gate. Let's see it in more detail with more understanding. So this test bench contains, as you can see, declaration of device and local signal. So guys, this test bench is using every design has a test bench of its own. For example, the AND gate we are testing, first it should have the declaration that where I am going to, I mean, what I am going to test in this test bench. So this test bench is also having the entity, but there will be nothing extra in the entity. We don't put anything because this test bench is only the test. It's not a kind of device under test. So the entity will remain empty because entity has declaration of input and output. Input and output is already coming from the design, from the component which we are testing. That's why the test bench entity will be remain empty, and then we have the declaration of the component which we are going to test. We are going to test AND gate, so we have to identify with the component keyword that this is my component which I am going to test. This component is the AND gate, and here, if you see, the name of the component is the entity name of my design. So in VHDL, the component is always the name of the entity. So here, my component name is the entity name of the design I am testing, and the same declaration of input and output what I have done in the design. And there, these are the internal signals of the test bench. These signal will be matched with the signals of my design. As you can see, these are the internal signals, and then I match my internal signals of the test bench with the signals of the design right here. So here I perform the mapping. So the component signal which I am going to test will be connected together with the signal of the test bench. And then here I applied my test cases. When I have 1 0, I will have something displayed on my graph area. Then I will wait 100 nanosecond. Then I say, okay, apply this input and get the output, wait again for 100 nanosecond, and then the last case. These are the test cases or the stimulus. So as you can see, first the declaration of device and local signal, which I am going to test, which is this part, this which is this part that I am having there. This is the my device. This is the test bench, which does not contain the outer signal but only will map some internal signals. That's why I have my component and the internal signal. And after that, what I do, these internal signals of the device will be matched with the holder. So it's called port mapping. So I have now the port mapping right here. And after that, I will have the testing. That will I will apply the plus minus from outside, and the output would be displayed inside the graph area. That whenever both of the input are one, only at that point I have output available. Otherwise, no. So in a test bench in VHDL, we have the test bench. I mean, in a normal FPGA project, we have a design file and a verification file. Design file is a file which contains my logic. Verification file is the file that contains my testing scenario. I mean, my testing code with the code which I am using to test. So in the test bench, which is also my testing file or verification file, we have an entity and it will remain empty. There will be no port because it's not designed, it's only testing. And then I have declaration of the component, that which component I'm going to use in this test bench. So, and after that, I have some internal signals. As you can see, test bench should have some internal signal which will be connected with the signals of the design. So I have to declare my internal signal and connect the internal signal of my test bench with my design signal. And then I will apply the different kind of test cases to get the output on the um, graph area. So if I explain the VHDL test bench, first section is the entity, remain empty. Next section will be the component which I am going to test. The third section will be the mapping of the signals, internal signals of this test bench with the signals of the device which I am going to test. And then I have to apply the input to get the graph or the simulation coming from my design. So this is I have. Is there any question so far, guys? Now the question arises, man, writing these test benches. I mean, of course, okay, the code is very simple. There is not more functionality or logic that you have to develop. You only have to declare some the component, signals, and then map them together and apply the different test cases to get the output. But even the file, I mean, it's too much code to write. And as you can see, if you have a design, generating this file is very easy. There is not very much logic. So there are some utilities available online where you will put the VHDL file, it will read the VHDL file, and it can generate the whole test bench automatically. Only thing that you have to provide the different test case scenario, the in different kind of input on which you want to see the output. Only you have to provide this thing. Then you can see the output in the simulation diagram. The test bench code is automatically generated. In the previous Xilinx version, they have this facility available. Now, somehow in the Vivado, they remove it. But we have some online tools. For example, one of the tool is available on this website. You can directly go into this website, put your VHDL code, it will generate the test bench and it will generate everything regarding this test bench. You only have to put in the stimulus area your inputs, that you provide the signal value 00, wait for some time, next, next, and so on. All the code is automatically generated. So now when we will do the simulation, first you will generate your design file, put the design file into this kind of utility, or write the whole code for yourself. These utilities are very good. So when you will put them, then you will have whole VHDL file. So now in Vivado, you will have your design file already ready, which you have worked. And outside, you generated this code, which should be present in the test bench file, because this is the test bench code. So after getting this auto generated code, you put this signal stimulus or signal test cases by putting the wait statements, that how much wait you want to do to apply the next test case, you can get the output. So now we have this code, and we have to include this code into our Vivado project. So first we had only this design file, and now for this design file, we will create the test bench. So you will right click on this project area of the sources in Vivado, and then previously we have clicked add or create design source. Now we will click add or create simulation sources. Click this option, and then when you will click, it will open another box that create the simulation file, name this file, and this file will be, when you click this option and move to the next, it will ask you put the name of the file, you give the name of the file, and then it will create another file which you can access in the simulation source. It will be an empty file, and there you can put the VHDL code which you generated already. So you first have to create this empty test bench file, which will be present after the creation in this directory, simulation sources sim1, and then this is a test bench. As you can see, this is the name I have provided, that this is my test bench, as you can see right here. And under this test bench, you will also have the link of this file, because this test bench belong to this design, and you don't, it will automatically come when the file will read your code which you have generated. So first you will generate this file. This file will be this one, empty. You put your generated code right here, save it. As soon as you save it, you will see this hierarchy, and from where it will come, because the Vivado will read that this test bench file is the test bench of this design, which you have created right here. And now you have the simulation file available. Save this file. And after this, you go to this simulation and click run behavioral simulation. When we had only design, after this design entry, we went to synthesis. But now we go to the simulation, click the simulation, run behavioral simulation, and then as soon as you run this behavioral simulation, if your VHDL code is right, it might be error. It might have an error because you might have put some kind of mistake when you have declared the signals right there. You can see that these statements are put by myself because I wanted to have 100 nanosecond and then apply this test scenario on my input and again wait and this test scenario. So if everything is fine, then it will generate this test bench. Otherwise, it will say to you that there is a problem, check it, and you correct this error and then run this behavioral simulation option again, and then you will see. So here you can see that whenever my input and output are 00, my my input are 00, output is 0. Again, when one input is 1, another one is 0, again I have my output 0. In this scenario, again, the only thing I have is this 1 1. Whenever I have both of the inputs are 1, then my output would be 1. So here in this test case scenario, I have only identified these two cases, but others are also present, that I have 4 scenario available. As you can see, 0 0, 0 1, 1 0, and 1 1. Can somebody tell me what is this? This orange? This orange is a condition which was there before this statement, because I said wait for 100 nanosecond. What was there? The level of input 1 and input 2. Nobody knows because it's not defined, undefined. That's why it is coming with this orange line. After 100 nanosecond wait, I define the different signals. So this is how you will perform this simulation for your VHDL code.